Hi students, very good morning. As an application of Gauss's law, we are going to discuss today how to arrive at an expression for the electric field due to an uniformly charged thin spherical shell. So you know already what is Gauss's law. So this is one of the applications of Gauss's law. That is electric field of an uniformly charged thin spherical shell. So let us consider a thin spherical shell which is charged uniformly. Say So let us say this is a thin spherical shell. Spherical shell in the sense, of course, it is hollow inside, and thereby we have some charges on the surface of the shell here. As we said, this shell is uniformly charged. Uniformly charged, you know what is the meaning of uniform charging. So it has a uniform charge density on the surface. Let us say that the surface charge density is sigma, and let O be the center of the shell, and its radius be, say, capital R be the radius. Now you know what is the charge density on this. Say if density is sigma, then what is the density definition? So definition of density, charge density is charge divided by surface area. So here, if I assume the charge to be some Q, then Q divided by A is the charge density, where A is the area, surface area of this shell, which of course Q divided by 4 pi R square. So this gives you the charge on the spherical shell to be sigma into 4 pi R square. So we have the charge on the shell here, which is sigma into 4 pi R square. Now we are going to find out the electric field at any point due to this spherical shell. And there are different possibilities. Maybe like the given point where you want to find the electric field is either outside the shell or inside the shell. So let us just find out as a case 1, field outside the shell. We will find out the field outside the shell. As you know now, Q is equal to sigma into, I'll keep this here, this is the charge, where sigma is the charge density. Now let me consider a point P. Let me consider a point P where I want to find the electric field. Say the point P is at a distance R from the center. Yes. Now, to find the electric field at P, we are going to apply Gauss's law. So, as I already told you, this topic is as an application of Gauss's law. So, what does Gauss's law say? Gauss's law talks about the flux through a closed surface. So, we need to have first a Gaussian surface. A Gaussian surface is a closed surface. Just to apply the Gauss's law, we consider an imaginary surface called as Gaussian surface. So now, at the point P, we need to find the field. Therefore, we will consider an imaginary surface which is passing through this point P, and it should have some symmetry with the system of charges. So the ideal is to consider a sphere, a spherical surface which is concentric with the given shell. I mean to say, if I consider a spherical surface this is an imaginary spherical surface to apply the Gauss law. Now this surface is concentric with the given shell, means the imaginary Gaussian surface and the given shell have the same center, and also the point P is lying on this Gaussian surface. So this is a Gaussian surface. Yes, see, any point on this surface is equivalent to the distribution of charges here, because already I told you that they are concentric surfaces. So every point, so either you take this point or any point here, you can understand that all these points are equivalent to this system of charges. I mean to say, so see, from this system of charges, all these points are equidistant also, and at the same time they are radial. So you can just look at the distances from the center of the shell also, so they are all same. So at every point on the surface, this shell of charges will have same effect. So thereby I can say, if the electric field here is E, then at any point on this surface, the electric field strength will be E only due to the shell of charges here. Now how to find the electric field there? So to get the electric field, so we will apply Gauss law. But to apply the Gauss law, we need to have an idea of the flux there. So for that, let me consider a small surface area here on the Gaussian surface, say delta S. Delta S is the area, an imaginary small area, infinitesimally small area we can say, delta S. So what is the flux through this surface? So you know that as every point is equivalent to the system of charges here, so you can say electric field here is either away from these charges or towards these charges based on the nature of charge. If I assume here positive charges, of course the field here is away in this manner, outward, radially outward, or if the charge here is negative, then the field is radially inward. That's the only difference. So every point will have the same effect. So at every point the electric field is radially outward or inward, we can say. Now at this point P, if E is the electric field strength, and by the symmetry of the system, as the E is radial, the normal to this surface and E are in the same direction. For this delta S, normal to the surface is this. At the same time, electric field strength is also in the same direction. So electric field and normal, the angle between them is 0. Now what is the flux through this small surface? Electric flux through delta S is, I will call it as delta phi is equal to E into delta S. That is by basic definition. Or E delta S cos theta you say usually. That is when theta is the angle between normal to the surface and electric field. Here normal to the surface and electric field angle is 0. Therefore cos 0 is 1. Now then you can say the total flux. So the complete Gaussian surface is phi is equal to summation delta phi, which is equal to summation E delta S, which is equal to E into summation delta S, which is equal to E into, now what is summation delta S? Sum of all these delta S areas. So it's an imaginary sphere on which delta S is a small area. If you add up all delta S areas, small areas, so you're going to get the surface area of the outer sphere. So surface area of the outer sphere is nothing but 4 pi r square. So this is the flux through the imaginary Gaussian surface. So I will call this as some equation 1. Now, by definition, we can get flux through any closed surface using Gauss's law also. So if I apply Gauss's law, now let me remove this. Let me just keep this equation as this. Now, applying Gauss's law, what is the flux through the closed surface, the imaginary surface? So it is simple. Phi is equal to 1 by epsilon naught times charge enclosed. 1 by epsilon naught times the charge enclosed by the surface. So what is the charge enclosed by this complete surface? I mean this imaginary surface. So that is the surface we are talking about as Gaussian surface. So within that surface, what is the total charge enclosed? Total charge enclosed is Q here, which is sigma into 4 pi r square. So that I will write here as 1 by epsilon naught into sigma 4 pi r square. How much is that? So this is nothing but sigma 4 pi r square by epsilon naught. This is equation 2. Now let us compare equation 1 and 2. According to by the general definition, due to the symmetry of this system, we tried to find out the flux through this closed surface, which is found to be phi is equal to E into 4 pi r square, where r is, remember, the radius of the outer sphere. So 4 pi r square is the area of that outer sphere. Anyways, that is understood. Now same way, we try to find out by applying Gauss's law the same flux, that is flux through the imaginary surface. So which is found to be sigma into 4 pi r square by epsilon naught, where r is the radius of the smaller spherical shell here. Now because both are LHS is same, that is where we have found out the flux through the same area. Now let us just compare these two. So comparing equations 1 and 2. So LHS is same, therefore sigma 4 pi r square by epsilon naught is equal to the another equation is E into 4 pi r square. E into 4 pi r square. So let me just remove this. Now from this you can understand, of course 4 pi cancels, then E is equal to, therefore E is equal to sigma by epsilon naught capital R square by small r square. I hope you understood this. So this is the electric field at a point P. But of course, once again, if you in case multiply by 4 pi in the numerator and denominator, you will find that sigma into 4 pi r square by epsilon naught into 4 pi r square. 4, let us not cancel 4 pi again, just multiply. So 4 pi r square is by definition what? The area of the surface area of the shell here. So, and this is the surface area of smaller, bigger spherical shell here. Now, sigma into, this is A I can say. So sigma, that is charge density into area, is nothing but charge, right? That is what it is. Sigma into 4 pi r square is Q divided by 4 pi epsilon naught r square. So this is the electric field. If I want the direction, I will put a vector symbol here and an r cap here, that is a unit vector, in the direction of the field, which is from our discussion here, radially outward, assuming that the charges are positive. In case if the charges are negative on the shell here, the electric field is radially inward. Therefore, this small r is either positive or negative, confirming that the field is either outward or inward based on the nature of charge, whether it is positive or negative. So this is the expression for electric field at a point outside the shell. Now you must have noticed one thing here. This is just looking like 1 by 4 pi epsilon naught into q by r square. What does that represent? It represents the electric field at a point due to a point charge at a distance r. Means if you have just one point so let me do this. So if you have one point charge q and at some distance r, if you have a point p, the electric field here is given by E is equal to 1 by 4 pi epsilon naught into q divided by r square, which is this. So a point charge, whatever a point charge gives, whatever the electric field given by point charge, same electric field is given here also by a spherical shell, which is having uniformly charged surface. So a uniformly charged spherical shell produces the same effect at any point outside in comparison to a point charge. Okay, so that's about the first case here. Now let us take the second case. So field inside this shell. Let us take inside the shell now. At any point inside the shell, let us consider the point P inside the shell. So I can just go ahead with removing this. Okay. Now let me consider a point P somewhere inside the shell. Say somewhere here. I'll take this as P dash. Or let me just remove this off. Right. Now, if the point P is somewhere inside, if the point P is somewhere here, the distance is say once again smaller. Now at point P, what is the electric field? Now we'll repeat the same whole thing once again. Whatever we did earlier, what did we do? We just considered an imaginary surface called Gaussian surface, which was passing through the given point P, and it was a closed surface which is concentric to the shell. Same thing we'll repeat here. So we'll consider imaginary Gaussian surface. So this is the Gaussian surface now. Imaginary Gaussian surface. What is the radius of the Gaussian surface now? Once again smaller, whereas capital R is the radius of the shell, which is charged uniformly. Now, what is the flux at point P? Of course, by general definition, flux at P is, I'll take phi is equal to E into or say summation E delta S cos theta, whatever you call it. Now you may be thinking, what is E now, what is delta S now, what is cos theta, everything. Of course, delta S is a small area here at point P where you want to find the electric field, and E is the electric field there. Cos theta is the angle between the electric field and the normal to that small surface delta S at that point by definition. That is all by definition. Don't worry more about this part. So let us just check the Gauss law here now. Applying Gauss law. So what is the flux? The flux through that imaginary Gaussian surface is phi is equal to 1 by epsilon naught times charge enclosed, which is equal to 0. Reason is there is no charge enclosed. There is no charge enclosed in this surface. Actually, the charge is residing on this spherical shell, right? It is not inside the shell. I already told you it is a thin spherical shell. Means it is hollow inside and it has a layered surface. Like. So I mean it's like a football. So charges are residing on the surface, not within the surface, not inside the surface. Therefore, within this imaginary surface, the total charge is 0. So therefore, flux is equal to 0. I will take this as equation say 4, equation 5. Now what is the two equations say here? So LHS is 5, RHS is 0. So compare the RHS. So equating 4 and 5. So we get E is equal to 0. So electric field is 0 at any point inside the shell. That is electric field of an uniformly charged thin spherical shell. Outside we found out what is the electric flux, which is just like that of a point charge, whereas within the shell, that is inside the shell, the electric field is 0. So there is no electric field inside a charged spherical shell. That's it. Thank you.